Okay.
Your line is now muted.
Thank you for attending the first webinar in the Zero Energy Ready Home series on the introduction to building science. This webinar will be recorded and the recording will be sent out to all attendees. If there are any issues with audio, please write in the chat, and that can be generated on the bottom of your screen, hovering over that little chat bubble. My name is Erica DeLello. I'm a project manager for NORESCO. This series is also sponsored by Walking Mountains and High Country Conservation Center. Jess Hoover is here to tell you a little bit more about each of those organizations. Jess, if you want to unmute yourself, go ahead.
Thanks, Erica. Thank you all so much for joining us today. My name is Jess Hoover. I'm the Climate Action Director for the High Country Conservation Center. We're an environmental nonprofit located here in Summit County, and we are proud to partner with NORESCO and the Colorado Energy Office on this webinar series to help our local community learn about the new sustainable codes we're implementing here. We provide a number of services across the county, not only climate action and energy efficiency, but also water conservation and waste reduction. To support the adoption of our new sustainable codes, we also provide the energy services that are on this slide. And we are partnering with Deeper Green Consulting, another local energy firm, to support a HERS Radar training in our community. So we are happy to support our local building professionals with code compliance, and we hope that you all learn a lot from these webinars and are able to adapt easily to the new codes. Walking Mountain Science Center is located in Avon and is helping us with this first webinar, and they also offer a number of energy consulting services across Eagle County. So thanks so much, Erica, and looking forward to Robbie's presentation.
Great, thanks, Jess. As she said, we've been working with the Colorado Energy Office to provide trainings just like this one. In addition to trainings, we've put together a code adoption toolkit that reviews cost implications of changing code cycles, the benefits, other compliance resources, and a lot more. So that is posted on the Colorado Energy Office's website. The link is posted on the screen now. We've also been working on a troubleshooting guide that covers I-code conflicts and alignments, clarifications, passive compliance. If you take the time to review these resources, feel free to provide feedback to me on items that could use more information that you think would be helpful to your jurisdiction or your company. On to the next slide is a list of upcoming trainings as well. You'll see the Zero Energy Ready Home series and a PUE webinar that's directed towards mountain communities. And if you have any projects in Denver County, there are also specific trainings available on their amendments as well. I will be sending you all a short survey at the end of the presentation with links to all of these trainings and resources. If you could please take the time to answer these survey questions, it will help us to continue to provide these trainings. Also, I have muted everyone's lines to reduce background noise, but sometimes WebEx does act up, so please mute your line on your end as well. We do want to encourage questions. So if you have any questions throughout, if you want to use the chat function, write your question in there and I'll let our presenter know at the end of the presentation. With that said, our presenter today is Robbie Schwartz. Robbie has been a champion of the building science industry for over 20 years. As principal of Build Tank Incorporated, Robbie works with builders of all sizes to ensure that their high-performance homes are efficient, healthy, and resilient. So with that, I'll let Robbie take the lead.
Thank you, Erica and Jess, so much, and thank you for supporting this webinar series and everyone joining in today to take part. It's going to be an exciting series, and we're just going to jump in today with regards to our introduction to building science. The Energy and Environmental Building Association put out this statement that says that residential construction is a complex operation including thousands of processes by dozens of industries, bringing together hundreds of components and subsystems into a house. I think it's a great statement to really demonstrate the complexity of the construction process for a single house, let alone a project of multifamily or bigger buildings, and that we have a lot of systems and components that are trying to come together, and how do we do that and also take into account performance in that equation. We see that in the past, we've been framing our houses since the late 1800s. We continue to frame our houses, and one of the big things that has changed really is the number of people that are taking part in the process. In the early or late 1800s, we framed our houses with really small family businesses that probably took it from foundation all the way through finished carpentry. Today, the National Home Builders Association has helped to, through some research, to determine that over around 300 people are taking part in building that house, and which really means that each individual trade partner, builder, architect has specialized at a specific function of putting that house together. And we have lost, to some extent, our ability to understand the holistic approach and understand how things go together in a holistic nature. Therefore, we've began to adopt systems and processes to help us build better houses. We also are seeing that our labor issues, supply chain issues, other issues that we have to deal with have made construction a little bit harder there. But our expectations of our houses have gotten more robust over time as well. You see some houses here that were built in the early 1900s, and right next to them houses that were built in our present day. And this really demonstrates how our expectations of our houses have changed, not only from an aesthetic perspective, but if we take comfort, for example, we see that people literally want to be able to walk around inside their home from room to room and floor to floor in their underwear and be quote unquote comfortable. That definition and quantification of comfort was quite different in the early 1900s. People were willing to work to create a comfortable home. They understood that they had to put on a sweater in the wintertime, potentially, put a log on the fire or shovel some coal to create a comfortable environment. Because that has changed so dramatically in our modern day housing, we've had to also change the way that we construct our houses and the way that we approach that construction of our houses. And what we see is that codes and programs have embraced this notion of applied building science and systems thinking, these two avenues to help us achieve house performance that we're trying to achieve today. This notion of applied building science is really looking at all of these different components and how do we integrate them together into a home to create a home that meets those core expectations that people have of their houses, core expectations of not only comfort, but long-term durability, energy efficiency, aesthetically beautiful homes, indoor air quality, and health and safety. All these different things need to be integrated into our houses. So we need to think about the envelope and ventilation and lighting and water efficiency and all these different things, and how do we integrate that. If we take one step further in the microscope and looking in this a little bit more closely, we ultimately see that the applied building science is really focused on airflow, heat flow, and moisture flow. So how do we get performance out of the house? How do we get long-term durability out of the house? How do we get additional efficiency out of the house? How do we meet those core expectations? Well, we have to be able to control heat flow, airflow, and moisture flow in order to do that, which leads us to kind of the systems approach and thinking process for how we approach the building of a house. It is this more holistic approach rather than a component approach, kind of going back to having a better understanding of the whole process of construction and how we integrate all these things together. Another thing that systems thinking does is really revolve around this word synergy. Synergy meaning two or more things that come together to achieve something greater than what could be achieved by itself or on its own. These core expectations that our buyers and builders of houses have are examples of being able to achieve something that we couldn't achieve before. How do we get that beauty, that comfort, that durability from a house? When we're adding complex heating and cooling systems, we're tightening up the building envelope, we're adding insulation to our systems. And in the past, doing those things has created building durability issues. Now we can do it if we change our approach and create a house that performs and doesn't have those necessarily have those building durability issues there. So systems thinking and synergy can be thought of in an example kind of by thinking about how we bring two components together. And normally when we bring two components of a building together, we generally have one outcome that we're trying to achieve. So for example, if I'm bringing insulation and an air barrier together, I'm thinking about how do I control heat flow through the building thermal envelope. Well, the reality is I'm also getting better air control in that house. And we'll be talking a little bit later on here how air impacts and what air does in our homes. But we need to know that we can be able to control heat flow and airflow if we properly install insulation and air barrier systems in our houses. We also get better moisture flow control, and we get better indoor air quality. So bringing these two simple components together, insulation and air barrier systems, we get a variety of outcomes from those two things. So that's the synergy that's brought into it. And thinking about that in the design phase early on in the project is what really becomes important. And as we move into more of the Zero Energy Ready Home program discussion and later in these series, we'll see that planning at the beginning of the process becomes really crucial to ensure that our execution of our goals for that house are able to be achieved there. So when we think about building systems integration, we can really think about 5 main components, beginning with the structure of our house, how we integrate the structure with the systems in our houses, from mechanical systems to insulation systems, from our enclosure, how do we keep water out of those systems and components, and then what specific climate we're building in. And then the fifth thing is how do the people interact with these other systems here, and how do we create this whole product that integrates the structure, the systems, the enclosure in the particular environment that we're building in, and how do we do that so that people will actually be able to use that? Because people tend to be the wild card in our equation here. People don't really know much about the house that they're moving into. They don't know what they don't know. They don't know necessarily that they need to change a furnace filter or do continual maintenance on the house. They care about maybe different things than we do in the construction industry. They have expectations of their houses, but how do we meet those expectations? We need to again, integrate this applied building science and systems thinking approach in order to meet those core expectations there. Okay. So we're building these houses in a specific climate, and the climate zone map that the IECC and the codes have developed helps us determine from a base case perspective how we begin to approach the building of a house in a specific climate. Our climate in Colorado, we're rather unique because we cover a lot of different climate zones here in Colorado. In the mountains, climate zone 6, 7, and 8. On the plains, primarily climate zone 5. The other thing about this climate zone map that we need to recognize is that there's a big dark line down the middle that separates the dry climate zones from the moist climate zones. And although we are located in the dry climate zones, moisture is still a pretty big issue from us. Maybe a little bit less from a humidity perspective. But we do have a lot of more humidity inside our houses than outside our houses, which might lead us to beginning to think about how we're constructing our houses because of the moisture drive that's happening there. So taking into account the climate that we're building in is very important, and some of the building science principles don't really change, but how we implement those principles could be slightly different in dry climate zones versus moist climate zones. The other thing we need to think about is that what's the impact of that climate zone on microclimates inside of our houses. When we're talking about microclimates, we're talking about moisture that's being impacted by temperature and humidity. And so we're trying to control that indoor environment to get better indoor air quality, to ensure that we're not getting the creation of molds or other things in our houses that are going to cause a problem in our houses. So when we're talking about gaining predictability and control, which we'll talk a lot about today, how do we get predictability and control? Well, from a building science perspective, we get predictability and control by tightening up our building envelope, by having good insulated building envelopes, having designed and well-executed mechanical systems, and having whole house control mechanical ventilation in our houses. And that control and predictability helps us manage the microclimates that we create inside of our houses within that bigger macroclimate of the climate zone that we're building in there. Microclimates are generally in moist areas that we're most concerned about, so kitchens, bathrooms, laundries, crawl spaces, basements, those types of locations that generally trap or are bigger moisture sources inside of our houses there. But the reality is that the whole house is a microclimate within the bigger macroclimate that we're building in. The ICC and all of these building programs really concentrate heavily on the building thermal envelope and trying to understand these different control layers, from water control layers, air control layers, vapor control layers, and thermal control layers inside our building assemblies. So the ICC has a new section that was developed in the 2015 cycle that says that the building thermal envelope shall be represented on the construction documents. This really highlights what's called, from a building science perspective, the red line test, which means that you want to be able to put your pen on a sectional drawing of your plans and continuously draw a line without taking your pen off that piece of paper around that building thermal envelope to ensure that you understand where the continuity of that thermal envelope is going to be, so that you can really get it, ensure that you understand where it's going to be and how you're going to execute that particular portion of the building thermal envelope. Now, the building thermal envelope is defined in the code as well, and we see that that definition is talking about all the different components, so that the thermal envelope really is an assembly of things that separate the conditioned space from the unconditioned space in our houses here. So we can see that that thermal envelope from a drawing perspective can be pretty straightforward, but when we're looking at that building thermal envelope inside the house, it might be difficult to determine exactly where we're going to have that building thermal envelope and how we're going to control, or how we're going to execute that building thermal envelope to get control and predictability of airflow, thermal flow, and moisture flow. So this picture on the left here, I'll try to orient you to that picture. We're standing on a bridgeway here, and over that railing is the open space of the living room down below. We have a loft area over to the right. We have that duct and duct chase, and then behind that is attic area above the bedroom below. So our question walking into this house might be, do we want that duct to be inside or outside the building envelope? And we should be saying that we want it inside the building envelope. So we're going to insulate this knee wall here to the attic. We're going to insulate behind the duct and this chase. We're going to insulate down this knee wall as well. We're going to sheathe this with drywall here. We're going to put drywall around this duct chase and down this wall here. And I would ask, is that duct now inside or outside the building envelope? Hopefully, we're all in agreement that it's still outside the building envelope because we haven't sheathed the attic side of this assembly here. We've insulated it, we've got the interior sheathing, but we need to get the exterior sheathing, and that adjacent to a ventilated attic would still be an exterior wall. But just adding that exterior sheathing tends not to be enough because I need alignment of my air barrier system and my thermal barrier system. And it turns out that the drywall around this chase is not in alignment with my thermal barrier, my insulation back in the cavity here. So I have to get a supplemental air barrier in that cavity here to bring that duct into the conditioned space of the house. So what the code is trying to do is ensure that we can do that red line test so that when we get into the field, we can identify areas where we need to put those supplemental air barrier systems into our home here. The air barrier systems, again, are defined here. We talk about the continuity of the air barrier system, and it's defined in the IECC. We talk about what an air barrier is. Again, it's one or more materials that join together continuously in a continuous manner, restrict or prevent the passage of air through the building thermal envelope. So we're really talking about assemblies of things. And often when we're talking about this air barrier system, we tend to think of it as one component, and often we think about it as just that component on the exterior side of the assembly. I'd like to challenge us to think about it more as a total assembly, which means that in its simplest form, we have interior drywall as a component of that assembly to be the interior part, and so we want to get the continuity of that interior part of our air barrier assembly. And then we have exterior sheathing as our exterior part of that air barrier assembly. And together, we get a true assembly that goes all the way around our building thermal envelope. Some may ask what's house wrap or other weather-resistant barriers. Well, they're primarily drainage planes because we know that moisture is going to bypass our siding. We need to be able to drain that water down and out. Therefore, although a drainage plane can be a supplemental air barrier and kind of a belt and suspenders type approach to building, we shouldn't necessarily rely on that house wrap or weather-resistant barrier to be our primary air barrier system unless we can ensure that it's going to be installed absolutely perfectly. And generally speaking, especially with house wraps, they're not installed well enough to be our primary air barrier system. So the function of this two-component, in essence, layer system for our air barrier system is not only to enclose the insulation, especially if we're using fibrous insulation where we need that stagnant pocket of air, but also to gain better air control, thermal control, and moisture control inside of our assemblies here. Now, the code helps us, and programs like Energy Star and the DOE Zero Energy Ready Home program have checklists that the code borrowed from to create this table that gives us an idea of where we might need that supplemental air barrier system, where the drywall might not be adjacent to our thermal barrier, and therefore we might need to add thermoply, or if we're using spray foam, that might be our air barrier system here. And all of these things, the code falls back on manufactured instructions, but there are some instructions in these tables and in these checklists from programs like Energy Star and the DOE program to be able to ensure that we've installed these things perfectly. But when we're talking about that air barrier system, the reality is that we're needing to create an air barrier assembly that has these 5 key attributes. Its continuity all the way around the building envelope, its strength, it's going to be durable over the life of the building, its stiffness, and its impermeability. Sometimes we want to use flexible air barrier systems, and often those flexible air barrier systems cannot be installed well to actually perform. So these 5 key attributes, if you stick with these 5 key attributes, you'll get a system that actually works. So moving into the applied building science section here, we're going to talk about thermal flow in our houses first, and then airflow, and then moisture flow. So if we break down thermal flow, we begin with the heat transfer mechanism with regards to thermal flow. The first law of thermodynamics says that energy cannot be created or destroyed, that energy moves and changes form, that heat flow is an energy transfer mechanism, and that energy equals work plus a change in that internal energy system, or what we call waste. That it's not that that waste is not energy, it's just that it's not being used for a useful purpose. An example of that would be a furnace, for example, where you have energy equals energy out plus that waste. So if I have a 100,000 BTU furnace and it's 90% efficient, then 90,000 BTUs are the output of that furnace, and 10,000 BTUs is the waste, of basically the amount that's going up the flue. So that would be an example of this first law of thermodynamics here. Now, the second law says that heat moves from higher temperature regions to lower temperature regions. That means basically always from hot to cold, or higher concentrations to lower concentrations. It never flows in the other direction unless you're adding additional energy to the equation. And no reaction, again, is 100% complete. So there is some energy loss or waste that we see in these equations here. As energy is transferred and transformed, more and more of it is waste. So we want to be able to get as much out of it in that first transition from its source to its purpose, so that we have the least amount of waste possible in that system there. Temperature and heat are also slightly different things. Heat is the form of energy, and heat is measured as the measurement of how energy is transferred from one system or body to another. So, for example, this dog's energy or heat is moving from the dog's body to the ice cubes, and it's actually the removing of that heat from the dog that's cooling the dog there. Now, temperature is a measure of the internal energy of a system, a measure of how fast the molecules are moving, and this is basically how we can measure it using a thermometer here. Heat transfer is the exchange of thermal energy between physical objects, so it's always moving, again, from hot to cold. And what we learn by understanding this is that things don't have to be hot necessarily to be able to move energy. And so when we think about a heat pump, for example, a heat pump can take energy, can move energy from one location to the other location, as long as there's higher concentrations of energy in one location versus the other location. So in very cold air, for example, it's amazing how much heat is in that, or energy is in that cold air, that you can actually extract and bring into a home during the heating season and heat a house. Some of these heat pumps can extract energy in air that's in the freezing temperature range. So it's pretty amazing here. This heat transport mechanism is one of the things that, and this temperature difference from inside to outside, are one of the key principles of what we call delta T, or the temperature difference, and the movement of energy from higher concentrations to lower concentrations. It drives our design temperatures for our heating, cooling, and ventilation systems, our HVAC systems. Whether you're doing hydronic heat or using a forced air system, you're going to use a design temperature that's usually a worst-case design temperature for heating and cooling of that structure, and that's where it's governed by. So to review just a little bit, the flow is always from higher concentrations to lower concentrations, and the higher the delta T, the greater the heat and air, the more, I guess, the heat and air wants to escape or enter a building there. So we need to remember those principles here. There are two types of heat. There's sensible heat. This is the heat that's able to be sensed by that thermometer, the heat that's absorbed or added or released by a substance, and this is the energy described by the heat load calculations, the manual J's that we do to create, to properly size our heating and cooling equipment inside our house. There's also latent heat that we don't have a lot of here in Colorado, but this is the heat that's released or absorbed by a substance during a change in phase. This is the heat or energy that's stored in moisture in the air often there. So that's why I say we don't have a lot of latent heat in Colorado, because we don't have a very humid climate here. This phase change is what describes latent heat. So when we're moving from a solid, like a solid ice cube, to liquid water, into vapor, that is the description of this latent heat transfer mechanism that happens there. Two kinds of energy: potential energy, which is the stored energy in wood or batteries or other systems, oil and gas, for example. And kinetic energy, this is the energy of motion, where atoms and molecules are in movement. The temperature of the energy is described by these atoms and molecules that are moving, that we can measure with a thermometer, for example. Okay, so how does this energy or heat move in our houses? It generally moves by conduction, convection, and radiant energy movement. And all of these things are happening simultaneously, but we're going to break them down one by one. And it's often helpful to understand a building durability issue or a building science question that you might have with your houses, if you can determine which is the most predominant heat flow mechanism that's happening through that particular piece of assembly. So understanding these things individually becomes important. Conduction is the energy that conducts through a solid object, always again from warm to cold, or from higher concentrations to lower concentrations. When we think of conductive energy, we think of energy generally in the wintertime. That's where we have a higher concentration of energy or heat inside of our houses, and it's moving through our assemblies from inside to outside, and we're using insulation to reduce that conduction through the building assembly. But we know that the energy will go more slowly through our cavity insulation, because it's a higher R value, than through our studs. So we're often struggling with how do we ensure that we're not getting large amounts of thermal bridging in especially cold climates where we're building in. How do we reduce that thermal bridging, or that area where energy is going to move faster through our studs or other components of our buildings, like foundations. Foundations, and if we're not dealing with that slab edge of that foundation, can be a large source of thermal bridging or bypass in our assembly. So we need to, again, think holistically about our whole house and where that thermal bridging is happening, and figure out details to be successful at slowing and stopping that thermal bridging, that thermal bypass through our assemblies. This particular detail is not an easy one to execute out in the field. That, how do you get that foundation insulation that's standing up above grade, but also going down to our footing? How do we protect that during construction and after construction? So it's a difficult detail, but these are the types of details that we need to start looking at an early stage of construction. Convection is the energy transfer of energy moving with fluids such as air or water there. Convective loops is an example of convective energy movement inside of our houses, inside of our wall systems. In a poorly insulated wall, you'll get energy or air warming on the warm side of the assembly. It goes up to the top plate, it rises as air warms, it rises. As air collects energy, it rises. It hits the top plate, it gets moved over to the exterior wall, and as it cools, it starts to fall, and you get this convective loop inside of a poorly insulated cavity insulation assembly there. So we want to ensure that our assemblies are insulated properly, that they're airtight, and we can control that convection portion of air moving in our houses. Convective air not only moves potentially in our wall systems, but in our houses. Convective loops are a good way of distributing heat around our houses or energy around our houses, but we want to make sure that we control that convective movement of energy so it's not moving outside of our houses. So energy moving with air, we want to control it inside the building envelope. So again, a tight structure. Properly insulated and sealed assemblies are largely how we do that there. So we need to think about, how do we achieve that assembly? So this was an interesting test situation that was done. They basically created a hot box or a foam box. On one side of the assembly, they had plexiglass and they had foam around it, and they had these insulated cavities. Inside the box, they had a high temperature at 140 degrees. So our question is, which cavity is performing best? And I think we would agree that the number one cavity is performing best here. And so which cavity, is it performing best because it has the highest R value or because the insulation was installed the best in that cavity? So when we break it down here, we see that the first cavity has an R11 bat. That was installed perfectly to a grade 1 or the requirements of code with a proper air barrier system on all 6 sides of the cavity here. Cavity 2 was an R19 cavity, so it had the highest insulation in the cavity, but it didn't have the best installation. It has this gap at the top, so we have some bypass around the insulation here. Cavity 3 is installed better than cavity 2 with less insulation R value, but it's performing better than cavity 2 with the higher insulation R value because it's installed better, had a better air barrier system, better bat install. And cavity 4 had no insulation in and no air barrier system to the inside. So this is just to show us that installation is really as important as R value. We need to make sure that we install the R value properly in order for it to perform there. And we'll talk about that in a little bit more here in a second. The last way that energy moves in our assemblies is by radiant heat transfer, and this is energy that flies through open spaces. So the biggest example of that is the energy that's moving from the sun to our planet through literally open space, or from a fire to our bodies on a cold summer evening. We might have that fire. And it's interesting to think about radiant heat transfer because it's a very linear pathway of heat movement. So if I'm standing by that fire, my front side might be nice and toasty, but my back side is going to be cold because the energy can't move laterally around my body. It moves linearly in a straight line there. Radiant barriers are sometimes used to help control this flow of radiant energy. We don't use a lot of radiant barriers in our climate, especially up in the mountains, but you have to think if you're seeing anybody recommending any type of radiant barrier below a slab or in an attic, you need an air gap in order for that radiant barrier to work here. But radiant energy does have a huge impact on our comfort inside of a home. This notion of mean radiant temperature is the notion that our body heat will radiate to colder surfaces that are inside of our home. So if I can raise the surface temperature of the surfaces around me, I can be more comfortable. In some cases, the picture on the right is trying to depict large areas of granite countertop. And that granite is a relatively cold surface. It's hard to warm up and keep warm. So I can be in my house, in my kitchen cooking, and I can actually be cold just because my body temperature is radiating to that cold surface of the granite countertop here, or radiating to the cold surface of a window as well. So these are things that are governed, that help govern our human comfort here. So we have the environmental variables, which are the air temperature, the relative humidity, air movement, and this mean radiant temperature, the things that surround us. If I get better control of these things, I'm going to have better comfort inside my houses. So again, building science and system thinking can help me do that. And there are the personal variables, the clothing we choose to wear, and our personal metabolic rate are impacting our human comfort as well. So when we think about these thermal transport mechanisms, we have to think about thermal transmittance. And this is basically how the building assemblies are dealing with conduction, convection, and radiant heat flow all at the same time there. But again, if we break them down, we often can figure out what's happening in a particular component of the building, because it might be driven more by conduction or convection or radiant energy flow than the other two. And if we can determine that, we might be able to determine how to fix an issue if we have a warranty issue, or if we're talking about an existing building, how to upgrade an existing building as well. Air sealing, from a code perspective, is largely looking at manufactured instructions for how we install the insulation inside of our assemblies. Codes and programs are generally relying on the code in this section as well. But when we're talking about insulation, just like insulation that we wear on our bodies, the object is to trap a pocket of air. It's the pocket of air that creates the R value, or the resistance to the flow of energy from warm concentrations to low concentrations. And ultimately, we need a stagnant pocket of air. Because if I wear this fleece jacket out on a cold and kind of windy day out there, the pockets of air that are being trapped in that fleece jacket are going to leave that fleece jacket, and I'm going to continue to be cold. So what do we do up in the mountains? We put on a layer of plastic, in essence, air barrier on top of the thermal barrier, or a shell on top of that thermal barrier there. So I have my interior air barrier, which is my skin. I have my thermal barrier, which might be a fleece jacket. And then I have an exterior winter shell that is my exterior air barrier system. And I'm able to trap that pocket of air. I'm able to stay out in the cold elements much longer. So similar to our houses, we've got a thermal barrier. Oftentimes it's a air permeable fibrous insulation that resists conduction, but it doesn't necessarily resist the flow of air through that assembly. So when we're talking about cavity insulation, we're talking about six-sided enclosures there, so that we can resist this myth of insulation, because insulation doesn't stop the movement of air itself. The object of that insulation is to trap a pocket of air, but I need that six-sided enclosure in order to ensure that that pocket of air is stagnant and I get the resistance to the flow of energy that is described by the R value material that's being installed. Okay, let's talk about airflow now, and let's break that down. How does air flow in our houses? I like to think about airflow as a freight train. If you think about a freight train, it's carrying a cargo from point A to point B. From an air perspective, it's also carrying cargo. It's carrying heat, it's carrying other energy, it's carrying moisture, and it's carrying pollutants. And the problem is that it's taking it from point A to point B as well, and we don't want it to deposit its load unless it's depositing a load all the way outside of the house. If it's depositing a load inside of our building assemblies, that's when we tend to get into trouble. Now, this question we get all the time, and hopefully everybody can agree that the answer to the question is no, that we're actually asking the wrong question, and we're ultimately trying to figure out how do we gain control of the airflow in our houses. That the tighter we build our houses, the better off we are, because we gain better control and predictability of the airflow and the cargo that air is carrying inside of our houses. So what is the real question we should be asking? We should be asking, are our houses underventilated? And the resounding answer still, unfortunately, is yes, our houses are underventilated. So this mantra ultimately becomes super important. We want to build tight and we want to ventilate right. We want to build as tight as we possibly can to gain control and predictability of airflow, moisture flow, and thermal flow, and ventilate correctly for the occupants, and also background moisture control inside of our houses. Codes and programs, the DOE Zero Energy Ready Home Program, and all the codes now understand this principle to varying degrees potentially, but they understand this principle, and building tight and ventilating right is required by all these things. So ultimately, you're trying to gain control and predictability control and predictability, similar to McDonald's when I go and order a Big Mac in Frisco or Denver or Paris, France, or New York City. I know exactly what I'm going to get. The predictability is astounding. I know what I'm going to get. I know how I'm going to feel after I eat that Big Mac. All these things are predictable here. So that's the type of control and predictability that we're trying to get. So when we're building a house, we need two things for that air to move in and out of that building thermal envelope. We need a hole, and we need some type of pressure difference around our house. Codes and programs are helping us understand how to control the holes in that building thermal envelope. We have a better chance and we have more ability to control holes in our building envelope than we ever have in the past, and we need to do that. So the other part are these building pressures that we get in our houses. So an example of that, if we look at a balloon here and we think of the rubber membrane in that balloon as our thermal envelope of the house, we see that what we ultimately want is equal pressure pushing in from the outside and pushing from the inside out there. And if I don't have a hole and I just have this pressure and it's equal on either side of our rubber membrane or our thermal envelope, then the air isn't going to move. But if I untie the string there and I create a hole, then the pressure outside is greater than the pressure inside, and I'm going to deflate that balloon, and air is going to move through the hole from inside the balloon to outside the balloon there. So we know that we have holes. We haven't yet been able to build a completely airtight house. We're getting better and better at that. But we also have constant pressures on our houses. We have this thing called stack effect, wind effect, and mechanical effect, or pressures on our houses here. So let's look at these individually. Stack effect just describes what happens to air as it warms. Again, we talked earlier, as air warms, it rises. And as it rises, it hits the top planes of our houses, the top boundary of our thermal envelope. And in essence, it's seeking a hole. If it finds a hole at a can light or a connection between drywall and the top plate or through a plumbing vent, it's going to leave the house. And any air that leaves the house has to be replaced by air coming back in. The picture on the right here demonstrates that the taller our buildings, the greater that stack effect is going to be. So in Denver anyway, we're starting to build these 3- and 4-story townhomes, and you can stand up on the top landing of a stairway system, and you can really feel the air rising up through that central chase coming up into that higher plane of the building here. So the accentuation of stack effect happens with the difference in the temperature, the greater the difference in the temperature from inside to outside, that delta T, but also because of the height of the building. But any air that leaves on the high side, it comes back in generally on the low side of our structures. So we often tend to concentrate on those high side holes and those low side holes in our building envelope. Wind is another kind of constant effect that's happening on our houses, or pressure that's being imposed on our houses. On the windward side, we generally get a positive pressure. On the leeward side, we get a negative pressure on our houses, and that pressure is translated through our building as well. So I can be pushing air into my home through holes in my building envelope, and I can be sucking air out of my building through holes in my building envelope, just because the wind is blowing there. So again, if I can control the holes, I'm not going to be able to control the wind out there, but if I can control the holes, I can control the air that's moving through those holes as well, and what that air might be carrying. Now, the last one we have is the mechanical systems in our houses. The mechanical systems in our houses create pressure differences in two ways. One would be individual room pressure differences, and then whole house pressure differences as well. Now, here's an example of pressure differences that are being created by unbalanced leakage in our duct systems that are located outside our building thermal envelopes. So on the return side, if I have greater return leakage, then on the supply side, I'm going to be supplying more air than I'm returning from the house. and therefore I'm going to be blowing that house up like a balloon slightly and pushing all the air against those exterior thermal envelope surfaces, and if there are holes, it will be going out of the house. If I have more supply side leakage, it reverses, so I'll get a negative pressure and I could be sucking air in from the outside. And so we need to think in Colorado, and especially up in the mountains, our air is generally drier outside than it is inside of our houses. So return side leaks could be even more detrimental to our houses because I'm pushing warm, moist air against those surfaces and potentially out of our houses there. So just to summarize, air is a fluid and will move if there's a path present and a pressure difference across that path. So if there's a hole or a driving force across that hole. Driving forces are just another way of talking about pressure difference across that hole. We need to remember that air in equals air out, and air out equals air in. If we have a quantity of air in our houses, we generally quantify that as a cubic foot of air in our house. How many cubic feet we have? A cubic foot is about the size of a basketball. Most houses have somewhere between 25,000 and maybe 60,000 cubic feet of air in our houses. If one basketball leaves, another basketball has to come back in to that house there. So this is a 100-year-old house, and we might ask, why is this house a 100-year-old house? Because it's drafty, it's uncomfortable, it's not necessarily meeting the expectations of the occupants of this house. Because it's not meeting those expectations, if we make changes to that building, we could be creating a big problem there. The main reason this is a 100-year-old house is that it has tremendous drying potential. So we're going to start moving into this notion of moisture control in our houses here. Now, our buildings, from a building perspective, things get wet, and we ultimately need to let them dry. They get wet from the outside, they get wet from the inside, they get wet from the start, and then there's the potential repeated wetting that's happening through condensation in our houses as well. Moisture flow transport mechanisms are gravity, capillary action, diffusion, moisture that's moving with air in its vapor state, and condensation in our buildings. So we need to deal with this moisture control issue. And it's one of the bigger control issues that we have on our houses because moisture is the #1 thing that destroys houses over time. So let's think about moisture in its vapor state and think, again, that air is a transport mechanism, therefore air and vapor are one. They equal the same thing here. When air moves, moisture is going to move with it. So in this example, I've got a typical back door here, and whenever we turned on the HVAC system in this house, we turned out to be pressurizing the house, and air would bypass this poorly weather-stripped exterior door, and when you opened up the exterior door, you'd see the condensation and ice forming on those cold surfaces there. So think again, not only if you have an HVAC system, but if the wind is blowing on your house, you might be sucking air out of a hole in your building envelope and creating problems. So being able to control the holes in our houses, making that a tighter house, we can control the potential condensation that's happening inside of our assemblies because air out equals air in, and air in equals air out here. Build tight. Now, again, the code and programs like Energy Star and the DOE Zero Energy Ready Home program have us looking at these details through checklists, or from a code perspective, it's asking us to actually detail out these air sealing details on our plan set so that they can be executed when we're building that house out in the field. Relative humidity is a really important part of this mechanism. We need to think about the amount of moisture that's held by air compared to the maximum amount that's possible. The maximum amount that's possible creates saturation or 100% relative humidity. So humidity is the capacity of air to hold water vapor, and it's a function of temperature. And if you can think about temperature as a towel and the size of the towel, then we can kind of have an understanding of what's happening here. So the warmer air is like having a bigger towel. It has the ability to absorb more of that moisture and hold it than it would otherwise. Absolute humidity is how much moisture is in the air by weight, and relative humidity is the amount of water vapor present in the air expressed in a percentage system of the amount that's needed for saturation to occur. So ultimately, how absorbent is that towel, and how saturated from a percentage situation is that towel? Is it 50% saturated, or is it 100% saturated where water's starting to pour out of the towel? The towel just can't hold any more of that moisture there. And this is becoming more and more important to understand because of some new research that's coming out there. From a building perspective, we ultimately want the air to be as dry as potential. We want as dry as possible, We want that air and that moisture content in that air, the relative humidity, to be low, because moisture potentially creates condensation, and moisture creates building durability issues with molds and other things in our houses. But from an occupant perspective, this new research is showing that the ideal relative humidity in our houses is in that 40 to 60% range, because it helps decrease infection, it reduces allergies, and improves healing in our bodies, and improves hydration in our bodies, and it can ultimately increase work performance. Now that we're working more from our homes, that could be an issue. So balancing ventilation with relative humidity and having better control and ensuring that relative humidity is not getting within our building assemblies is becoming more and more a crucial thing that we need to think about, because we potentially want higher humidities for occupant health in our houses there. But again, needs to be balanced with health of our buildings as well. Moisture control is primarily an issue because we're trying to control mold growth in our houses, which is very hard because there's mold everywhere in our houses. Mold needs wood or paper-based products to grow, and we have a lot of those, but it can also grow on paints and insulation and carpets and other areas of our houses. We need that mold spore and the nutrients, but ultimately we need moisture, and if we can control the moisture and the temperature in our houses, we can generally control the mold growth that's happening in our houses. So again, we need to control moisture control, thermal control, and air control in order to ultimately have a home that can control mold growth in our houses. So ultimately, we want to promote drying mechanisms over wetting mechanisms. The other ways that moisture moves in our houses, we've talked about water vapor moving with air, but we need to talk briefly about bulk water, capillary action, diffusion, and condensation in our houses. Bulk water, we generally have control over. We understand that we want to let that water hit our structure, be able to drain down, and then ultimately, using gravity, drain that moisture away from our houses. It's all about execution and how well we do those exterior water control layers on our houses. So we're using different weather-resistant barriers, the new zip systems, potentially foam sheathing, liquid-applied membranes or house wraps, all these different things to control that bulk water. And ideally, we're using some type of vented rain screen technology to be able to give at least a 3/16 air gap to allow that moisture to move down and potentially dry out behind our first source of protection, which is our exterior siding, and then our second source of protection, which would be that true water control layer on that exterior of our homes. Capillary action or capillary breaks is trying to keep moisture moving through generally our concrete building materials up and into our houses, into our wood assemblies there. So it's important not only to understand how capillary action moves through the pores, moving water up through the pores of our materials, but what materials are actually capillary breaks and what aren't capillary breaks, and where do we install those materials. Sill seal is a great example of that because it is primarily a capillary break. It generally is not installed well enough, or our foundations aren't level enough and or we shim the sill plate, so we often aren't getting good enough air sealing through that sill seal installation. But that sill seal is crucial from a capillary break perspective. So we want it installed well, but we have to remember to come back to this location and air seal it properly per the instructions in the code tables and the checklists from programs to get that air sealing done there. And then we need to think about the true capillary break at our footing to foundation wall or underneath our slabs to get the right capillary breaks in the right locations there. Vapor diffusion is a process of that vapor not necessarily moving with air, it's moving directly through the pores of materials, generally from higher concentrations to lower concentrations. Because we have more moisture inside our houses than outside our houses, we see that this moisture is moving directly through the pores of drywall primarily, from higher concentrations again to lower concentrations, and it's a function of temperature and the percent of relative humidity, that higher concentration to lower concentration. What we've learned through a number of experiments, this being the main one that's been done over and over again, is that there's more vapor transport by air leakage than there is by the process of diffusion. Over the course of a heating season where we had 70-degree air with 40% relative humidity, only a third of a quart of water was able to diffuse through this sheet of drywall versus 3 quarts of water that's able to move through one inch square hole. And remember, if you're not using airtight outlet boxes, you have about 1 square inch of net-free area every 6 to 8 feet around your house. So getting that control and predictability, we want to seal up those boxes and make sure that air isn't carrying moisture into our assemblies, because the process of diffusion is pretty small, especially after you've painted that wall and you have a class 3 vapor retarder in there. But if moisture is getting into those assemblies, either by diffusion or from air leakage into that assembly, we're worried about that first condensing surface. What's the temperature of that exterior sheathing? And is that moisture going to condense and turn into its liquid state? And that liquid state is the danger state. If we can keep it in its vapor state, it has the ability to potentially dry back out or diffuse back out of the assembly. But if it hits its water state, it's just going to be absorbed by that material, and repeated wetting is what's going to create the molds and destruction of those assemblies. So this is a dew point calculator. It's based off of a psychrometric chart, and it tells us that if we have 35% relative humidity at 70 degrees, and that air hits a temperature, a surface temperature that's 40 degrees, we're going to get condensation in that assembly. So how do we raise the surface temperature of those condensing surfaces here? One way to control this is to add vapor retarders, but if we add vapor retarders and we don't deal with the air leakage, then we're going to get moisture that bypasses those vapor retarders in our assemblies, and they're going to trap moisture in those assemblies. Another way to deal with condensation is to build tighter homes and either control the surface temperature or control the relative humidity in the house, or do both. And so controlling surface temperatures might mean, controlling diffusion might mean installing vapor retarders much better than we normally do, ensuring that we're overlapping seams and taping it, that we're putting vapor retarders up against our openings and sealing it to those openings, using outlet boxes that have flanges that we can seal it to, and installing vapor retarders continuously around the envelope and not just haphazardly around the envelope there. Or we can increase the surface temperature of our surroundings, or we should be doing both really. And this could be done by lowering the U value of our windows or putting exterior foam sheathing on the outside, all these different methods of increasing the surface temperature to reduce condensation. And this was a new voluntary test that can be recognized on the NFRC labels of the windows that we achieve that gives the condensation resistance for that particular surface there, which I thought was kind of interesting. So again, our key area barrier details, we need to have continuity, strength, durability, stiffness, and impermeability to stop the movement of moisture with air. And then when we're talking about vapor management from a diffusion perspective, we want to talk really about drying. How do we encourage drying mechanisms over wetting mechanisms? How do we avoid using vapor barriers, where vapor retarders will provide enough performance? How do we avoid using vapor retarders when vapor permeable materials provide satisfactory performance? Avoiding the installation of vapor barriers on both sides of our assemblies, unbeknownst to us. So we need to start this planning in the planning stage and material specification stage to understand the vapor permeance of our materials. How do we avoid vinyl wall coverings and encourage proper ventilation in our systems, in our systems to ensure that we have control here. Okay, in conclusion, again, starting early in the process with a systems thinking and applied science, building science solutions perspective, how do we plan properly to build that house so that we can control and gain better predictability of heat flow, airflow, and moisture flow in our houses? We know that the codes and the programs that we're dealing with are asking us to build a well-defined building thermal envelope that has continuity of the insulation and air barrier system all the way around it, and that all the control layers are in continuity, especially the moisture control layer, all the way around our building assemblies. The codes and programs that we're dealing with have incorporated this applied building science, and we need to take advantage of understanding what the codes and programs are asking us to do early enough in the process so that we can ultimately execute it well out in the field. So thanks so much for taking some time to discuss this with me today. If you have questions, I'm more than happy to stick around and answer questions, or you're more than welcome to email me or give me a call and ask any question that you might have.
Thanks, Robbie. That was great. As Robbie said, we will stay on the line. I know we're a little bit over on time right now, so if you have to go, no worries. But we will stay on the line for the next 2 minutes. If anyone does have any questions, feel free to unmute your line and ask, or write in the chat, and Robbie can answer it. But otherwise, thank you for attending today. And our next portion of the series is on Thursday for a program overview of the Zero Energy Ready Homes. So feel free to join us then as well, and thanks again for coming.